Welcome to Chapter 5 of our exploration into the fascinating world of machine intelligence. In this chapter titled Ethical Dimensions of AI Evaluation, we will delve into the critical intersection between artificial intelligence and ethics. As we advance in developing sophisticated AI systems, especially large language models, LLMs, it becomes imperative to consider the ethical implications of our creations. This isn't just about technological progress. It's about ensuring that the AI we integrate into society operates in ways that are fair, transparent, and accountable. The increasing integration of AI into various facets of our lives brings about both opportunities and challenges. AI systems are now influencing decisions in healthcare, finance, law enforcement, and more, with such significant impact. Ensuring that these systems do not perpetuate biases or operate opacely is not only a technical necessity but a moral imperative. Ethical considerations must be woven into the very fabric of AI development and evaluation to foster trust and acceptance among users and stakeholders. In this chapter, we'll embark on a comprehensive journey to understand the ethical dimensions of AI evaluation. We'll begin by exploring the concepts of bias and fairness in AI systems, examining how biases can manifest and the consequences they entail. Understanding these facets is crucial for developing AI that doesn't inadvertently reinforce societal inequalities. We'll discuss metrics and techniques for measuring and mitigating bias, equipping you with the tools to assess fairness in AI applications. Next, we'll delve into the importance of explainability and transparency in AI. As AI models become increasingly complex, the need for transparent decision-making processes grows. We'll explore methods for achieving explainability, discussing both inherently interpretable models and post hoc explanation techniques. Transparency isn't just about building trust. It's about empowering users and stakeholders to understand and challenge AI decisions, ensuring they align with ethical standards. Finally, we'll address the crucial aspect of accountability in AI systems. We'll examine mechanisms for ensuring that AI developers and organizations are held responsible for their creations. This includes exploring ethical guidelines, regulatory frameworks, and technical solutions that promote accountability. Through case studies, we'll highlight real-world scenarios where accountability measures have been implemented, emphasizing their importance in responsible AI deployment. By the end of this chapter, you'll have a deeper understanding of the ethical challenges in AI and the approaches to address them. Our goal is to equip you with knowledge that goes beyond technical proficiency, fostering an ethical mindset essential for anyone involved in AI development or utilization. So, let's begin this vital conversation on ensuring that our advancements in AI contribute positively to society. In this chapter, we will navigate through several key areas essential to understanding and addressing the ethical dimensions of AI evaluation. We'll start with an introduction that sets the stage for why ethical considerations are paramount in the era of advanced AI systems. This will provide context on how AI's growing influence in society necessitates a focus on fairness, transparency, and accountability. We'll then delve into bias and fairness metrics, exploring how biases manifest in AI systems and the impact they can have on individuals and groups. We'll discuss methods for measuring bias and fairness, providing you with practical tools and concepts such as disparate impact, equal opportunity, and demographic parity. Following that, we'll examine techniques for mitigating bias, offering insights into pre-processing, in-processing, and post-processing methods that can reduce biases in AI models. Our journey continues with a focus on explainability and transparency measures. Here, we'll understand the importance of AI systems being interpretable and transparent to users and stakeholders. We'll explore various methods for achieving explainability, including both inherently interpretable models and post hoc explanation techniques like feature importance and saliency maps. Ensuring transparency is not just a technical challenge but also a pathway to building trust in AI systems. Lastly, we'll discuss ensuring accountability in AI systems. We'll explore mechanisms for ensuring accountability, such as ethical guidelines, standards, and regulatory frameworks that are emerging globally. This section will highlight the roles of different stakeholders, from developers to governmental bodies, in promoting ethical AI practices. By the end of this chapter, you will have a comprehensive understanding of the ethical landscape in AI and the practical steps needed to navigate it effectively. As we stand on the cusp of an AI-driven era, the integration of AI systems into society brings not only technological advancements but also profound ethical considerations. AI is no longer confined to research labs. It influences everyday decisions, from loan approvals to medical diagnoses. This pervasive influence means that the ethical dimensions of AI are more critical than ever, demanding our immediate attention and action. One of the paramount concerns is ensuring that AI systems are developed and deployed in ways that are fair and just. Bias in AI can lead to unjust outcomes, disproportionately affecting certain groups and entrenching existing inequalities. Such biases can erode trust in AI technologies, hindering their adoption and the benefits they can bring. Therefore, addressing bias is both a moral responsibility and a practical necessity for the sustainability of AI advancements. Transparency and explainability are also central to the ethical deployment of AI. As AI models, especially deep learning systems, become more complex, their decision-making processes often resemble black boxes that are inscrutable to users and even developers. This opacity can lead to skepticism and fear, particularly when AI decisions significantly impact people's lives. Providing clear explanations and ensuring transparency can build trust, facilitate acceptance, and allow for meaningful oversight and accountability. Accountability in AI is another critical dimension. With AI systems making autonomous decisions, it's essential to establish mechanisms that hold developers and organizations responsible for the outcomes of those decisions. This involves not only technical solutions but also legal and regulatory frameworks that define responsibilities and consequences. Accountability ensures that ethical considerations are not an afterthought but an integral part of AI system design and implementation. This chapter aims to navigate these complex ethical landscapes, offering insights into how we can measure and mitigate bias, achieve transparency, and ensure accountability. By exploring these dimensions, we empower ourselves to develop AI systems that are not only intelligent but also align with our societal values and ethical standards. Together, we can steer the development of AI in a direction that maximizes its benefits while minimizing potential harms. Bias in AI systems is a multifaceted issue that can profoundly impact the fairness and equity of automated decisions. One form of bias is algorithmic bias, which arises from flaws or limitations in the algorithms themselves. This can occur when the algorithm's design or parameters inadvertently favor certain outcomes or groups over others. For example, if an algorithm weighs certain features more heavily without appropriate justification, it might produce skewed results that disadvantage specific populations. Another significant source of bias is data bias. AI models learn from the data they are trained on, and if this data is not representative of the diversity found in the real world, the models can develop biased behaviors. For instance, a facial recognition system trained predominantly on images of light-skinned individuals may perform poorly on recognizing darker-skinned faces, leading to discriminatory outcomes. Data bias reflects the societal biases present in the data collection processes and historical records. Human bias also plays a crucial role in AI systems. Developers and data scientists bring their own conscious or unconscious biases to the table, influencing how models are built, what data is selected, and how results are interpreted. These biases can seep into AI systems through decisions about feature selection, labeling, and even the framing of the problem the AI is intended to solve. Without awareness and proactive measures, human biases can become embedded in AI technologies. The consequences of bias in AI are far-reaching. Biased AI systems can lead to unfair outcomes for certain groups, such as denying loans to applicants from particular demographics or misdiagnosing medical conditions based on race or gender. They can reinforce social inequalities by perpetuating historical patterns of discrimination present in the data. Moreover, the erosion of trust in AI systems becomes inevitable if users perceive AI decisions as unfair or discriminatory, which can impede the adoption of beneficial technologies. Understanding the various forms of bias is the first step toward mitigation. It requires a comprehensive approach that addresses algorithmic design, data collection, and the human factors involved in AI development. By acknowledging and dissecting these biases, we can work towards fairer AI systems that serve all members of society equitably. To address bias effectively, it's essential to have robust methods for measuring it within AI systems. This involves developing and applying specific metrics that quantify bias and assess fairness, providing a foundation for identifying discriminatory patterns and evaluating the impact of interventions aimed at reducing bias. By systematically measuring bias, we can move from anecdotal observations to evidence-based strategies for promoting fairness. One of the key concepts in this realm is disparate impact, which refers to situations where AI outcomes disproportionately affect certain protected groups, even in the absence of intentional discrimination. It's measured using the Disparate Impact Ratio, which compares the rates of favorable outcomes between protected and unprotected groups. A ratio close to 1 suggests that outcomes are being distributed fairly, while significant deviations indicate potential bias that needs to be addressed. Disparate treatment differs from disparate impact in that it involves intentional discrimination, where an AI system explicitly uses a protected attribute, such as race or gender, to make decisions. Identifying disparate treatment involves examining whether the AI system treats individuals differently solely based on these attributes. This form of bias is particularly concerning as it violates principles of equality and often legal standards against discrimination. Other important concepts include equal opportunity and equalized odds. Equal opportunity focuses on ensuring that true positive rates are equal across different groups, meaning that individuals who should receive a positive outcome have an equal chance of doing so, regardless of their group membership. Equalized odds goes a step further by requiring both true positive and false positive rates to be equal across groups, providing a more comprehensive measure of fairness. Lastly, demographic parity, or statistical parity, requires that positive outcomes are distributed equally among different demographic groups. While it is a straightforward concept, it may not always be appropriate, as it doesn't consider the context or underlying differences between groups that might justify different treatment. Therefore, it's crucial to use demographic parity in conjunction with other fairness metrics to gain a holistic understanding of bias in AI systems. By employing these metrics, developers and researchers can quantify bias, identify unfair practices, and track the effectiveness of mitigation strategies. Measuring bias is a critical step in the ongoing effort to create AI systems that are fair, equitable, and just. Disparate impact occurs when an AI system's outcomes disproportionately affect certain protected groups, even without intentional discrimination. This unintentional bias can arise from imbalanced training data or systemic issues within the algorithm. Measuring disparate impact involves calculating the disparate impact ratio, which compares the probability of a positive outcome for the protected group to that of the unprotected group. A ratio close to 1 indicates fairness, suggesting that the system's decisions are not adversely impacting one group over another. For example, if an AI hiring tool recommends male candidates significantly more often than female candidates, there may be a disparate impact based on gender. Understanding and identifying disparate impact allows organizations to investigate and address the underlying causes of these imbalances. Disparate treatment, on the other hand, involves intentional discrimination by the AI system against certain groups. This occurs when the system explicitly takes protected attributes into account in a way that disadvantages individuals from those groups. For instance, if an AI loan approval system denies application simply because the applicant belongs to a certain race, it is engaging in disparate treatment. Addressing disparate treatment requires ensuring that AI systems do not use protected attributes in decision-making unless legally and ethically justified. It also involves auditing systems to detect any intentional biases that may have been introduced during development. Understanding the distinction between disparate impact and disparate treatment is crucial for developing strategies to mitigate bias. Both forms can lead to unfair outcomes, but they require different approaches for detection and correction. Ensuring that AI systems are free from both unintentional and intentional discrimination is essential for ethical and fair AI deployment. Continuing our exploration of bias and fairness in AI systems, let's delve into two pivotal concepts: equal opportunity and equalized odds. These principles are essential in ensuring that AI models make decisions that are fair and non-discriminatory across different groups. Equal opportunity focuses on providing all groups with an equal chance of receiving a positive outcome when they are qualified. In the context of AI, this means that the true positive rates, the rate at which qualified individuals receive a positive decision, should be the same across protected and unprotected groups. Mathematically, this is expressed as the probability of a positive outcome given a positive label, indicative of qualification, and belonging to a protected group being approximately equal to that for an unprotected group. This ensures that, for those who deserve a positive outcome, their group membership does not disadvantage them. On the other hand, equalized odds extends this fairness criterion by requiring that both true positive rates and false positive rates are equal across different groups. This means that not only should qualified individuals have an equal chance of a positive outcome, but unqualified individuals should also have the same likelihood of not receiving an undeserved positive outcome, regardless of group membership. Equalized odds addresses potential disparities in error rates, ensuring that one group is not disproportionately subjected to false positives or false negatives. Implementing these concepts involves adjusting the AI model to balance these rates across groups. This might require modifying the decision thresholds or incorporating fairness constraints into the model's optimization process. The goal is to achieve a balance where the model performs equitably for all groups, minimizing both types of errors in a fair manner. However, pursuing equal opportunity and equalized odds can introduce trade-offs with overall model accuracy. Adjusting the model to meet these fairness criteria might lead to a reduction in performance for certain groups or the model as a whole. This necessitates a careful consideration of the ethical implications versus the practical performance of the AI system. Understanding and applying these fairness metrics is crucial for developing AI systems that promote equity and fairness. By striving for equal opportunity and equalized odds, we can work towards mitigating systemic biases, ensuring that AI decisions are just and that all individuals are treated equitably by automated systems. Building upon our discussion of fairness metrics, let's explore demographic parity, also known as statistical parity. Demographic parity requires that an AI system's positive outcomes are distributed equally across different demographic groups, regardless of any individual qualifications or characteristics. Specifically, the probability of receiving a positive outcome should be the same for both protected and unprotected groups. This fairness criterion is straightforward to measure and implement. By calculating the proportion of positive outcomes in each group and comparing them, we can assess whether the AI system is treating groups equally in terms of outcome distribution. If disparities are found, adjustments can be made to align these probabilities, promoting equitable treatment. However, demographic parity may overlook important context-specific considerations. For instance, if one group has a higher prevalence of certain qualifications or risk factors, enforcing equal outcome distributions might lead to unfair advantages or disadvantages. It doesn't account for legitimate differences that could justify divergent treatment based on relevant attributes. An alternative approach is fairness through unawareness, which suggests that AI systems should not use protected attributes, like race or gender, in decision-making processes. The idea is that by excluding these attributes, the system cannot discriminate based on them. However, this method has limitations. Even if protected attributes are omitted, the AI system might still infer them indirectly through correlated variables, leading to biased outcomes. Moreover, completely ignoring protected attributes can prevent AI systems from making corrections that would counteract existing biases in the data. In some cases, incorporating protected attributes thoughtfully can help the system adjust for historical inequalities, promoting fairer outcomes. Balancing demographic parity with other fairness considerations is essential. While equal distribution of positive outcomes is a noble goal, it must be contextualized within the broader framework of equity and justice. Combining demographic parity with metrics like equal opportunity and equalized odds can provide a more comprehensive assessment of fairness, guiding the development of AI systems that are both fair and contextually appropriate. Having discussed how to measure bias and fairness, let's turn our attention to the practical steps we can take to mitigate bias in AI systems. Mitigation strategies are crucial for developing AI that is fair, trustworthy, and aligned with ethical standards. These techniques can be categorized into three main approaches: pre-processing, in-processing, and post-processing. Pre-processing techniques involve modifying the training data before it's fed into the AI model. The goal is to reduce or eliminate biases present in the data, thereby preventing the model from learning and perpetuating them. Methods include data augmentation, where underrepresented groups are amplified in the dataset to balance representation. Reweighting adjusts the importance of certain data points during training, giving more emphasis to instances from protected groups. Synthetic data generation creates new data points that mirror minority groups, enriching the dataset's diversity. In-processing techniques focus on the model training phase. These methods modify the learning algorithms to incorporate fairness constraints directly into the optimization process. Fairness constraints and optimization adjust the objective function to penalize unfair outcomes, guiding the model to prioritize both accuracy and fairness. Adversarial debiasing involves training the model alongside an adversary that attempts to predict the protected attribute. The main model aims to make accurate predictions while the adversary fails, thus reducing dependency on biased attributes. Fairness-aware regularization incorporates additional terms in the loss function to discourage biased behavior during training. Post-processing techniques are applied after the model has been trained. These methods adjust the model's outputs to achieve fairness without altering the internal mechanics of the model itself. Recalibrating probabilities modifies the predicted probabilities to ensure that the distribution of outcomes aligns with fairness criteria. Re-ranking results rearranges the outputs to balance representation, which is particularly useful in recommendation systems. Fairness-aware decision rules set thresholds that vary by group to equalize error rates or positive outcome rates across different demographics. Each of these techniques has strengths and limitations. Pre-processing methods are model-agnostic and address bias at its source but may result in loss of information. In-processing techniques can achieve a better balance between fairness and accuracy but require access to and modification of the training algorithm, which isn't always possible. Post-processing methods are easier to implement but might not fully address inherent biases within the model. Implementing bias mitigation strategies requires a nuanced understanding of the specific biases present and the context in which the AI system operates. Often, a combination of techniques yields the best results. By actively employing these methods, developers can create AI systems that make fairer decisions, promoting equity and reducing the risk of perpetuating societal biases. As AI systems become more sophisticated and pervasive, the need for explainable AI, XAI, grows increasingly important. XAI refers to AI models and methods that make the decision-making processes of AI systems transparent and understandable to humans. This explainability is crucial for several reasons, impacting trust, regulatory compliance, and the overall efficacy of AI deployment. Firstly, trust and acceptance are foundational for AI adoption. Users are more likely to trust and rely on AI systems when they understand how decisions are made. Transparency in AI fosters confidence, especially in high-stakes areas like healthcare, finance, or criminal justice, where decisions can have significant personal impacts. Secondly, explainability aids in bias detection. By understanding the internal workings of AI models, stakeholders can identify potential biases or unfair patterns in decision-making. This insight is essential for correcting discriminatory practices and ensuring that AI systems operate ethically and equitably. Thirdly, compliance with regulations necessitates explainable AI. Laws such as the General Data Protection Regulation (GDPR) in the European Union require organizations to provide explanations for automated decisions that affect individuals. Explainable AI enables organizations to meet these legal obligations, avoiding penalties and maintaining public trust. Moreover, explainability contributes to accountability. When AI decisions are transparent, it's possible to assign responsibility and hold relevant parties accountable for outcomes. This is particularly important when errors occur or when decisions lead to adverse consequences. Clear explanations allow organizations to address issues promptly and effectively. Finally, explainable AI enhances safety and debugging. Understanding how AI systems make decisions helps developers detect errors, vulnerabilities, or unexpected behaviors. This facilitation of continuous improvement ensures that AI systems remain reliable and perform as intended over time. In summary, the importance of explainable AI cannot be overstated. It is a critical component in building ethical, trustworthy, and effective AI systems. By prioritizing transparency and understandability, we can maximize the benefits of AI while mitigating risks and fostering positive relationships between AI systems and the societies they serve. One effective way to achieve explainability is by using inherently interpretable models. These are models designed with transparency at their core, enabling users to understand and trace the decision-making process without complex post-hoc analysis. Let's explore some examples of such models. Decision trees are perhaps the most intuitive interpretable models. They represent decisions and their possible consequences in a tree-like structure, where each internal node denotes a test on an attribute, each branch represents the outcome of the test, and each leaf node represents a class label or decision. This visual representation allows users to follow the path from input features to the final decision, making the reasoning process clear and accessible. Linear models, such as linear regression and logistic regression, are also inherently interpretable. In these models, the output is a linear combination of the input features. The coefficients associated with each feature directly indicate the strength and direction of its influence on the outcome. By examining these coefficients, users can understand which factors are most significant in the model's predictions. Rule-based models use a set of if-then rules to make decisions. These rules are derived from the data and represent logical conditions that lead to specific outcomes. For example, in a medical diagnosis context, a rule might be, if symptom A is present and symptom B is absent, then the diagnosis is condition X. Such models closely mimic human reasoning and are straightforward for users to interpret. The advantages of inherently interpretable models are significant. They are easy to understand, allowing users without technical expertise to grasp how decisions are made. This accessibility fosters trust and enables stakeholders to validate and challenge the model's reasoning. Additionally, the transparent decision-making process facilitates the identification of biases or errors, supporting ethical standards and regulatory compliance. However, there is often a trade-off between interpretability and predictive performance. Inherently interpretable models may not capture complex nonlinear relationships as effectively as more complex models like deep neural networks. Despite this, they are invaluable in applications where explainability is paramount, and the potential costs of opaque decision-making are high. In conclusion, inherently interpretable models play a crucial role in the ethical deployment of AI. By ensuring transparency from the outset, they help build trustworthy systems that align with societal values and user expectations. In contexts where understanding the rationale behind decisions is essential, these models offer a compelling solution. When inherently interpretable models are insufficient for the complexity of a task, AI practitioners often turn to more complex models like deep neural networks, which are typically less transparent. To address the need for explainability in such cases, post-hoc explanation techniques are employed. These methods are applied after model training to interpret and explain the predictions of complex, black box models. One common technique is feature importance analysis. Tools like SHAP, S-happily additive explanations, and LIME, local interpretable model agnostic explanations, quantify the contribution of each input feature to the model's output. By assigning importance scores to features, these methods help users understand which variables are most influential in the decision-making process. This insight can reveal whether the model is relying on appropriate factors or if it's being unduly influenced by irrelevant or biased features. Saliency maps are particularly useful in image recognition tasks. They highlight regions of an input image that were most significant in the model's prediction. By visualizing these regions, users can see what the model paid attention to when making its decision. This helps in verifying whether the model is focusing on meaningful aspects of the image or if it's misled by spurious patterns. Counterfactual explanations provide insights by showing how slight changes in input features can alter the model's output. For example, in a credit scoring system, a counterfactual explanation might indicate that increasing an applicant's income by a certain amount would change a loan application from rejected to approved. This helps users understand the reasoning behind decisions and what factors could lead to different outcomes. Model distillation involves training a simpler, interpretable model to approximate the behavior of a complex model. By capturing the essential decision-making process of the original model, the distilled model provides an accessible explanation while retaining much of the predictive power. This approach bridges the gap between performance and interpretability. These post-hoc techniques offer several benefits. They provide insights into black box models, making complex AI systems more transparent and understandable. This aids in debugging and improving models, as developers can identify and address issues related to feature influence or unexpected behaviors. Furthermore, these explanations support compliance with regulations requiring transparency in automated decision-making. However, it's important to acknowledge that post-hoc explanations may not capture all nuances of the model's reasoning and can sometimes be misleading if not properly validated. Therefore, combining multiple explanation methods and critically evaluating the results is essential for gaining a comprehensive and accurate understanding. Transparency in AI systems extends beyond model interpretability. It encompasses the entire lifecycle of AI development and deployment. Implementing practices that promote openness and clarity is crucial for building trust, facilitating oversight, and aligning with ethical and legal standards. Documentation is a foundational aspect of transparency. Maintaining detailed records of data sources, model architectures, training procedures, and evaluation metrics provides a clear trail of how the AI system was developed. Comprehensive documentation allows stakeholders to understand the choices made at each stage, assess the system's validity, and identify potential areas of concern. Auditability is another key element. By enabling independent audits of AI systems, organizations allow third parties to examine and verify the system's functionality and compliance with ethical guidelines. This involves maintaining logs of model decisions, data usage, and versioning. Auditability ensures accountability, as it provides a mechanism to trace decisions back to their origins and assess their appropriateness. Effective stakeholder communication is essential for transparency. Communicating clearly with users and stakeholders about how the AI system works, the data it uses, and its limitations fosters trust and collaboration. Addressing concerns and ethical implications openly helps mitigate misunderstandings and builds a foundation for responsible AI use. Producing transparency reports is a proactive way to share information publicly about the AI system's functionalities, performance, and ethical considerations. These reports can include details about data collection, model behavior, bias mitigation efforts, and impact assessments. By making this information accessible, organizations demonstrate a commitment to openness and invite feedback from the broader community. Finally, adopting open-source models where possible can enhance transparency. Sharing model code and methodologies allows other researchers and practitioners to scrutinize, replicate, and build upon the work. This collaborative approach accelerates innovation and helps ensure that AI development proceeds in a transparent and ethical manner. Ensuring transparency in AI systems is a multifaceted effort that requires intentional practices and a culture that values openness. By prioritizing transparency, organizations not only comply with ethical norms and regulations but also build stronger relationships with users and stakeholders, paving the way for AI systems that are trusted and embraced by society. Accountability is a cornerstone of ethical AI deployment, ensuring that those who develop and deploy AI systems are held responsible for their outcomes. Establishing accountability involves adhering to several key principles that guide responsible practices and foster trust among users and stakeholders. Responsibility entails clearly defining who is accountable for the AI system at each stage of its life cycle. This includes developers, managers, and organizations who design, implement, and manage AI technologies. By assigning roles and responsibilities, it becomes possible to address issues effectively when they arise and ensure that there is ownership over the ethical dimensions of the AI system. Transparency is critical for accountability, as it allows stakeholders to understand how decisions are made and to evaluate the fairness and appropriateness of those decisions. Openness in AI processes and decision-making fosters trust and enables oversight, ensuring that AI systems are used responsibly. Fairness is a fundamental ethical principle requiring that AI systems treat all individuals equitably and without discrimination. Ensuring fairness involves actively working to identify and mitigate biases, promoting equal opportunities and outcomes across different groups. This commitment to fairness upholds ethical standards and complies with legal requirements related to discrimination. Privacy is essential in protecting individual rights. AI systems often process personal data, and safeguarding this information is critical. Respecting user privacy involves implementing robust data protection measures, complying with data protection laws, and being transparent about how personal data is used. Safety and security are paramount in preventing harm from AI systems. This includes ensuring that AI technologies are robust against errors, failures, and malicious attacks. Implementing safety protocols and security measures protects both users and organizations, maintaining the integrity and reliability of AI systems. By integrating these principles into the development and deployment of AI systems, organizations can establish a framework for accountability that promotes ethical practices. This not only helps prevent negative outcomes but also enhances the reputation and trustworthiness of the organization, contributing to the sustainable and responsible advancement of AI technologies. In the rapidly evolving field of AI, establishing ethical guidelines and standards is crucial for aligning technological advancements with societal values. Various organizations have taken steps to create frameworks that guide the responsible development and deployment of AI systems. Professional organizations, such as the IEEE, have initiated efforts like the IEEE Global Initiative on Ethics of Autonomous and Intelligent Systems. This initiative brings together experts to develop comprehensive guidelines that address ethical concerns, including transparency, accountability, and human rights. These guidelines serve as a reference for practitioners and encourage the integration of ethical considerations into AI engineering. Governmental bodies play a significant role in setting standards. The European Commission's Ethics Guidelines for Trustworthy AI is a prominent example, outlining key requirements for AI systems to be lawful, ethical, and robust. These guidelines emphasize respect for fundamental rights, societal values, and the importance of human oversight. Industry consortia and collaborations among tech companies have also developed codes of conduct and best practices. These industry-led initiatives, such as the Partnership on AI, aim to encourage responsible AI innovation and share knowledge across organizations. By fostering a collective commitment to ethics, these consortia help standardize practices and raise the overall standard of AI development. The key elements of these guidelines typically include promoting transparency, ensuring that AI systems are understandable and open to scrutiny, fairness, preventing discrimination and promoting equitable treatment, accountability, holding developers and organizations responsible for AI outcomes, and privacy, protecting individuals' personal data and respecting their rights. Adopting ethical guidelines and standards provides organizations with a framework for addressing ethical challenges proactively. They offer practical recommendations and tools for implementing ethical principles, helping organizations navigate complex decisions and avoid potential pitfalls. By aligning with recognized standards, organizations demonstrate their commitment to responsible AI, fostering trust and credibility. Ultimately, these guidelines and standards are essential for ensuring that AI advancements contribute positively to society. They encourage a thoughtful approach to innovation, where ethical considerations are integral to the development process, leading to AI systems that are not only technologically advanced but also align with human values and societal well-being. As we delve deeper into the ethical dimensions of AI evaluation, it's crucial to understand the role of regulatory frameworks in shaping the responsible development and deployment of artificial intelligence. Regulatory frameworks provide the legal backbone that ensures AI systems are aligned with societal values and legal standards. They serve as the enforceable guidelines that organizations must follow, promoting fairness, transparency, and accountability on a systemic level. One prominent example is the General Data Protection Regulation (GDPR), enacted by the European Union. The GDPR is a comprehensive data protection law that governs how personal data is collected, processed, and stored. It has significant implications for AI systems, particularly those that involve automated decision-making processes. Under the GDPR, individuals have the right to understand and challenge decisions made by AI, and organizations are required to implement appropriate safeguards to protect personal data. In the United States, legislative efforts such as the proposed Algorithmic Accountability Act aim to increase transparency in automated decision-making systems. This act would require companies to assess and mitigate risks associated with their AI systems, especially those that could result in biased or discriminatory outcomes. By mandating regular audits and impact assessments, such regulations strive to hold organizations accountable for the ethical implications of their AI technologies. Globally, many countries are recognizing the need for AI-specific regulations to address the unique challenges posed by advanced AI systems. These emerging laws focus on aspects like bias mitigation, explainability, and the ethical use of AI in sensitive areas such as healthcare and criminal justice. The development of these regulatory frameworks is a testament to the growing awareness of AI's potential impact on society and the importance of proactive governance. Understanding and complying with these regulations is not just a legal obligation, but also a step towards building public trust. Organizations that prioritize ethical practices and adhere to regulatory standards are more likely to gain the confidence of users and stakeholders. As AI continues to evolve, staying informed about regulatory developments is essential for anyone involved in the field, ensuring that AI advancements contribute positively and responsibly to society. Moving beyond regulations, technical solutions play a pivotal role in ensuring accountability within AI systems. These solutions provide the practical tools and methodologies that developers and organizations can implement to monitor, explain, and rectify the behaviors of AI models. By integrating accountability measures into the technological framework, we create systems that are not only compliant with ethical standards but also robust and trustworthy. One fundamental technical solution is the implementation of audit trails. Audit trails involve systematically recording all aspects of the AI system's operation, including data usage, decision-making processes, and model versioning. By maintaining detailed logs, organizations enable traceability, allowing them to review how specific decisions were made and identify any deviations from expected behavior. Audit trails are invaluable for diagnosing issues, investigating incidents, and demonstrating compliance during audits. Another important aspect is the use of explainability tools. Techniques such as SHAP, happily additive explanations, and LLM, local interpretable model-agnostic explanations, help interpret complex AI models by highlighting how different features contribute to predictions. These tools make it possible to understand and communicate the reasoning behind AI decisions, which is essential for transparency and building user trust. They also aid in identifying potential biases or errors within the model. Bias detection and mitigation tools are also critical technical solutions. These tools help identify instances where the AI model may be exhibiting biased behavior. By analyzing the model's outputs across different demographic groups, developers can detect unfair patterns and implement corrective measures. Some tools offer automated bias mitigation strategies, integrating seamlessly with the development pipeline to promote fairness from the outset. Monitoring systems provide continuous oversight of AI performance and compliance. By setting up real-time monitoring, organizations can track key metrics related to fairness, accuracy, and ethical adherence. Alerts can be configured to notify stakeholders when the system deviates from acceptable parameters, enabling prompt intervention. This proactive approach ensures that AI systems remain aligned with ethical standards throughout their operational lifecycle. Finally, robust security measures are essential to protect AI systems from malicious attacks and unauthorized access. Implementing strong authentication protocols, encryption, and intrusion detection systems helps safeguard sensitive data and maintain the integrity of the AI models. Security is a foundational aspect of accountability, ensuring that the AI system's actions are genuine and free from external manipulation. To truly grasp the importance of accountability in AI, let's examine some real-world case studies that highlight both the challenges and effective practices in this domain. These examples illustrate the tangible impact of AI systems on society and the critical need for ethical oversight. One notable case is the Compass recidivism prediction tool, used within the criminal justice system to assess the likelihood of a defendant reoffending. While intended to aid in fair sentencing, the tool faced significant criticism due to alleged racial biases. Investigations found that the system disproportionately labeled minority defendants as high risk compared to their counterparts, even when controlling for prior offenses and other factors. This case underscores the consequences of deploying AI without adequate bias detection and the importance of transparency in revealing how such decisions are made. In response to ethical concerns, some organizations have taken proactive steps to ensure accountability. Google's AI Principles and Ethics Review is a prime example. Recognizing the profound influence of their AI technologies, Google established a set of guiding principles focused on fairness, privacy, and accountability. They implemented an ethics review board tasked with overseeing AI projects, ensuring they align with these principles. This institutional commitment reflects an understanding that ethical considerations must be integrated into the organizational culture and processes. Another example is the healthcare company's deployment of an AI system for patient diagnostics. Faced with the potential for life-altering decisions, the company prioritized explainability and accountability. They implemented comprehensive audit trails and used explainability tools to ensure clinicians could understand and trust the AI's recommendations. Regular audits and compliance checks were established, involving cross-disciplinary teams to maintain ethical standards. This approach not only enhanced the system's reliability, but also fostered trust among medical professionals and patients alike. These case studies highlight the multifaceted nature of AI accountability. They demonstrate that technical solutions must be complemented by organizational policies and a commitment to ethical practices. Transparency, open communication, and willingness to address shortcomings are key factors in successfully managing the ethical dimensions of AI systems. Learning from these examples, we can better navigate the complexities of AI deployment and strive for systems that are both innovative and ethically sound. As we conclude this chapter on the ethical dimensions of AI evaluation, it's clear that the journey towards responsible AI is both challenging and imperative. The integration of AI systems into critical aspects of society necessitates a steadfast commitment to ethical principles, ensuring that technology serves humanity equitably and justly. Addressing bias and fairness is not just a technical hurdle but a moral obligation. By diligently measuring and mitigating biases, we can prevent the perpetuation of social inequalities and foster systems that treat all individuals with fairness. This requires ongoing vigilance, as biases can emerge from data, algorithms, and human influences. The importance of explainability and transparency cannot be overstated. These elements are foundational for building trust between AI systems and their users. By making AI decisions understandable and processes transparent, we empower individuals to engage with technology confidently and responsibly. Transparency also facilitates oversight and accountability, essential components in maintaining ethical standards. Ensuring accountability involves a multifaceted approach, combining regulatory compliance, technical solutions, and ethical governance. Organizations must take proactive steps to establish clear responsibilities, implement robust auditing mechanisms, and cultivate an ethical culture. Accountability ensures that when challenges arise, they are addressed promptly and appropriately, reinforcing the integrity of AI systems. The road ahead involves continuous learning and adaptation. As AI technologies evolve, so too must our ethical frameworks and evaluation methods. Collaboration across disciplines, bringing together technologists, ethicists, legal experts, and more, is vital for developing comprehensive approaches to the ethical challenges we face. In embracing these ethical dimensions, we not only enhance the performance and acceptance of AI systems but also affirm our commitment to leveraging technology for the greater good. By prioritizing fairness, transparency, and accountability, we pave the way for AI innovations that uplift society, respect individual rights, and contribute meaningfully to the advancement of humanity.